Hello, everyone. My name is Felipe Oliveira Franco. I am a postdoc researcher at the University of Oxford. And in this talk, I will present a little bit about my work on phase statistics. More precisely, I will present the first measurement of phase correlations on real data. And this work is a collaboration with David Alonso here in Oxford, and also with Boriana Hadzinska from Harvard University. And you can find the paper related to this talk on arXiv, looking for this reference number. So I start with my motivation, which is the large scale structure. When we look at the distribution of matter in the late time universe, we see a complicated structure made of clusters, filaments, sheets, and voids, and they form the cosmic web. So this is clearly a signature of a strongly non-Gaussian field, and it has a lot of information concerning the evolution of our universe, the nature of gravity, and so on. That's why one important question in modern cosmology is how can we extract this non-Gaussian information? And in fact, this can be quite challenging for some reasons. And for instance, there is no optimal statistics in terms of data compression. For high order correlators, the number of independent modes grows, so the data analysis can be complicated, and there is a lack of analytical solutions. So this implies that it's difficult to derive theoretical predictions. So in this context, phase correlation could be an alternative approach to tackle this problem. So in configuration space, the statistic of a random field is given by the endpoint correlation functions, and in Fourier space, we have the Fourier modes and the polar spectra. So in the polar representation, the Fourier mode can be written in terms of an amplitude and a phase. And the idea behind phase correlation is actually very simple. So for the Gaussian case, the statistics of the field is completely described by its power spectrum. And the power spectrum depends only on the amplitude. So in this case, phases are uniformly distributed, and we say that there is no phase information for the Gaussian case. On the other hand, non-Gaussianities can introduce phase couplings. So part of this non-Gaussian information can be described by phase correlations. So here, epsilon of R is the inverse Fourier transform of the phase factors. And the phase factors are the exponential of the phase, or if you prefer, it's the Fourier mode divided by its amplitude. So here we have an example from n-body simulation. So with Gaussian initial conditions, there is no phase information, but as the time evolves, the correlation between the phase appear. And one example is the line correlation function, which is defined as the phase correlation of 3 equidistant points in a straight line. So previous work have shown that this observable, it can be useful. It can break the degeneracy between the growth rate f and the amplitude of the perturbation sigma a. Moreover, it was studied in the context of redshift space distortion and also in the context of modified theories of gravity. But the main idea here is that the line correlation is sensitive to the filamentary structures in our universe. And my motivation on the observational side is that in the future, photometric galaxy surveys will play an important role in cosmology. They will probe the late time structures, and their project map will still preserve the underlying and non-Gaussian structure. So basically, that's our motivation for this work, which is to measure the phase correlations on the sphere. Here, I formally introduce our observable, the projected line correlation function. So this is my definition. Our observable is defined as the phase correlation of three equidistant points lying on a great circle. So due to the symmetries of this configuration, the line correlation function depends only on this angle theta here. And because now our field delta is defined on a sphere, instead of using Fourier transform, we use spherical harmonic transform. So we can see here what is our definition for the phase factors. Okay. So the data that we have used to measure our observable is the 2MPZ, and this is an almost all sky galaxy catalog extract from the two mass by cross-matching with two additional data sets, SuperCosmos and WISE survey. And the reason we chose 2MPZ is first, it's a photometric catalog, and also because it has a low redshift. So this means that we still can see the filamentary structures of the cosmic web in this projection. So this is our final sample in galactic coordinates. So you can see here the filaments, they are evident. This sample, as I said, has low redshift, has high photometric accuracy, and to avoid systematic fluctuations such as stellar contamination, we mask out 32% of this sky, mainly the galactic plane here, and the resulting F-sky factor is 0.68. And this is a very important thing for us because we have to estimate what is the impact of the mask in the line correlation. So since we are working with a spherical harmonic transform, the mask will couple the modes affecting both the shape and the normalization of the line correlation. But here we propose a simple approximation, which is given by an overall normalization of F-sky, as you can see here. And the way we compute our estimator is given by this expression. So epsilon is the phase map at a given unmasked pixel. Big theta is a top hat function. Delta theta is the angular beam, and this is how, and that's our estimator. Okay, so we validate our approximation, we have to test it. So we run 100 fast simulations using the code Colore. And in this plot here, you can see the mean and the scatter of those simulations. So in red, we have the full sky case. In blue is the masked case, and in yellow, the yellow dots are our approximations. So we can see by this plot here that our approximation, it's indeed very good, and it's able to take into account the effect of the sky incompleteness. So we can proceed. And in this work, to build a theoretical prediction, we use the high performance antibody simulation from Abacus. So we construct mock galaxy catalogs from 100 different halo occupation distribution models. So in this framework, we vary two parameters. This parameter here, M min, which characterize the minimal halo mass to host a central galaxy, and the other parameter is M1, which characterize the typical halo mass that hosts one satellite galaxy. And we consider those range here. So, and to estimate the covariance matrix and the error bars, we use the jackknife resampling method, and we see that the covariance for the line correlation has large off-diagonal elements that must be taken into account. And we also got from the data a non-negligible covariance between the power spectrum and the line correlation, which is sourced by high order correlators. And this is our covariance matrix. And here I present the measurements both for angular power spectrum and line correlation function. So the black dots in both plots are the data from 2NPZ. The red solid line shows the joint best fit model, and the colored band shows the predictions when we fix the parameter M1 to this value here and vary M min, the other parameter. And as a result, we estimate the statistical significance of the first measurement of the line correlation function with a signal to noise of 6.5 sigma. And finally, we quantify the additional information contained in the line correlation by constructing this Gaussian likelihood here. So Q is our HOD-free model parameters, and M is the theoretical model provided by the Emulator, and C is the jackknife covariance matrix. And for the data D, we consider three different cases: the angular power spectrum alone, the line correlation function alone, and the combination of them. And here is the most interesting plot of our paper. The contours shows 68 and 95% confidence level. And in red, we have the power spectrum case. We see that there is a strong degeneracy between our parameters M min and M1, and the direction of this degeneracy roughly coincides with the constant bias isocontour. And for the line correlation function alone, which is the blue contour, we still have this degeneracy. However, what is interesting is that the direction, it's different when we compare to the power spectrum. And that's the explanation why we find better constraints when we combine both. So in black here, we can see that we are able to improve the final constraints on our parameters, and that's the main result of our paper. And therefore, we obtain the following marginalized constraints for M min and for M1 here. And that's our result. So finally, my conclusion is that we present here the first measurement of phase correlation on real data, we have shown that the addition of the line correlation is able to improve the parameter constraints, and in general, this advocates the use of phase correlation in cosmological data analysis. And as future perspective, maybe we can apply these to three-dimensional data sets. This can be quite challenging, but we expect some interesting results from phase correlations. And the final remark is that here we have focused on one specific kind of phase correlation. Maybe other phase correlation configurations may contain valuable cosmological information. And that's it. I would like to thank all the members of the Oxford Cosmology Group, my collaborators, and also the Swiss National Science Foundation for the financial support. And if you have any questions, I will be happy to chat on the discussion sections, or if you prefer, you can send me an email. Thank you very much.